In the last video, we were talking about standard deviation, S of x, and that's still standard deviation. So we've got one that is the statistic and the other that is a parameter. Statistics are from samples, and parameters are from populations. Remember, we take a sample from a population, all right? The nice part is they both start with the same letter. Statistics starts with S, parameters starts with P as in populations. So if I look at the mean, the symbol for mean in a statistic is x bar. For a population, it's mu. If you are a part of mu alpha theta, you might have heard of that. It sounds like a funny cat meow, mu. Standard deviation for a sample is S of x, and for a population, it is sigma, S-I-G-M-A. Now, the neat part is that there's actually a relationship between these two, and we can look at it by looking at the formula for standard deviation. For a sample, it's the sum of the squared deviations divided by n minus 1. Take the square root. For a population, and actually let's look back here. You see that we have that where we're dividing by n minus 1, and then we took the square root. For a population, instead of dividing by n minus 1, we divide by n. So if we solve for both of these, here we got n minus 1, and we use n minus 1 for technical reasons. I won't go into the derivation here. And then we use n for the population. So we can actually solve these for sum of the squared deviations. And this will lead us to a neat relationship between the two. So we're squaring both sides. Then we can cross multiply so that we can get S of S on one side. Okay, now since I have both sides here equal to the sum of the squared deviations, I can just set up one equation with both pieces. I'm going to go ahead and have n minus 1 S of x, so the sample side is n times sigma squared. All right. Now I'm going to go ahead and solve for sigma because I'm trying to create a relationship between the population and the sample. And if I take the square root of both sides, then that gives me just sigma. Now I have that S of x squared, so that can kind of pop out. It's just S of x. So what this tells me is that if I take a sample standard deviation and I want to find the population, all I have to do is multiply it by the square root of n minus 1 over n. So if n were, say, we'll do a different table here. If n were some different values, so let's say 10. All right. And then I substitute into the formula. I'll have 9 over 10, which is the square root of 0.9. If n is 100, then I'll have the square root of 99 over 100, which is the square root of 0.99. If I put in 1,000, then take the square root of that, it's the square root of 0.999. So what number am I approaching? The number I'm approaching is 1, which means that for very large n's, if n gets very big, and if you took a pre-cal and did limits, then n minus 1 over n kind of goes to 1, which means the square root of 1 is 1, which tells me for very large samples, the population standard deviation and the sample standard deviation are pretty much going to be the same. Oh, there's one other thing. You might want to go ahead and solve for sigma squared, because sometimes it's actually easier to use the squared standard deviation. This is the variance instead of the standard deviation, because when you square a number that you round, you're not necessarily going to get the same thing. For example, if I square 2.17, I will get roughly the variance. But if I square 2.2, I will be off. So when you work, please try to work with the variance first and then the standard deviation.